Hello there, Mr. Sutton here, bringing you the BC Calculus 7-8 Extra Practice Number 4 solutions on interval of convergence. To find the radius of convergence on this one, the key is recognizing that we can rewrite all of this as one big fraction, x minus 2 over 10, to the nth power. If we do that, we see that this is actually a geometric series with an r value of x minus 2 over 10. So for a geometric series to find the radius of convergence, we just need the common ratio here, the absolute value of that, to be less than 1. And then we just need to get this to have x with a coefficient of 1. Once we do that, whatever's on the other side of this inequality is going to be the radius of convergence. So to get a coefficient of 1 on x, I just have to multiply everything by 10. So I can write absolute value of x minus 2 is less than 10. And then the radius of convergence is just this 10 here. To find the radius of convergence for this series, since this is not quite a geometric series, we're going to have to use the ratio test. So I'm going to have the limit as n approaches infinity of absolute value of, and now we need the n plus 1th term over the nth term. So for the numerator of our big fraction here, we're going to have all of this stuff with n plus 1 replacing n. And we're actually going to forget about this negative in front here, since this is all inside a big absolute value anyway. So I'm just going to write 2 to the n plus 1, and then this is going to actually be n plus 2, and this is going to be x minus 1 to the n plus 1. Now in the denominator, we're just going to have 2 to the n plus 1, and x minus 1 just to the n, just the nth term, a positive version of everything you see here. And now we can actually just cancel some things out right away. So with these 2's, using my exponent rules, I'm going to cancel out all but 2 to the first power in the numerator. And with these x's, the only thing left over after I cancel these x minus 1's here is going to be an x minus 1 to the 1 power, also in the numerator. So we have a 2, an n plus 2, and an x minus 1 upstairs. Downstairs, the only thing left is this n plus 1. And now if I multiply things out, I've basically got... and by the way, if I let n approach infinity, I can ignore this plus 2 and this plus 1. So we essentially have a 2n and an x minus 1 upstairs. Downstairs, basically just an n. Again, if you ignore these slower growing parts of these n terms. So the n's are going to cancel. We really just end up with 2 parentheses x minus 1 left over when all is said and done. So for the series to converge, this this nth term ratio, this nth ratio here, has to be less than 1. And to get the radius of convergence, we just have to get this set up so that we have a coefficient of 1 for x. So to do that, we just have to divide everything by this 2. That'll give us x minus 1 inside, and we'll have a 1/2 on the other side. Once we've done that, whatever's on this other side here, when x has a coefficient of 1, this other number over here is going to be your radius of convergence. So that's just going to be 1/2. To find the radius of convergence, we're going to have to use the ratio test on this because it's not a geometric series. So we need to find the nth ratio. So we have the limit as n approaches infinity of absolute value of, and now we have n plus 1th term over the nth term. So n plus 1th term is going to be x plus pi to the n plus 1, all over radical n plus 1. And downstairs we just have the nth term, so basically the stuff we see in the original summand here. Same change flip, we've got x plus pi to the n plus 1 times radical n in our numerator. Downstairs we've got x plus pi to the n times radical n plus 1. And these x plus pi terms can cancel a bit, so I'm only going to have an x plus pi to the 1 power in the numerator, and this whole n plus pi to the n is gone because you basically did n or x plus pi to the n plus 1 minus n, so that got rid of all these. So upstairs then we just have x plus pi and radical n. Downstairs you just have radical n plus 1. As n approaches infinity, we can ignore this plus 1 inside, so you essentially have a radical n and another radical n that can cancel out at that point, leaving us with only x plus pi, because this x plus pi thing, this is treated as one big constant. All right, so in order for the series to converge, this nth ratio we have to be less than 1 for that absolute value. And that means that since we have a coefficient of 1 on x, whatever's on the other side is our radius of convergence. So in this case, that's just going to be 1. To find the interval of convergence for this series, I'm going to first rewrite this. Since I have a bunch of stuff to the nth power in the numerator and 4 to the nth in the denominator, I'm actually going to unmultiply everything by this nth power. And just going to rewrite this as x minus 1 squared over 2, all of that being raised to the nth power. So when I rewrite it like this, I can very clearly see that we have this repeated multiplication by this one term here. This is a geometric series. Our R value is going to be x minus 1 squared over 4. That being the case, to find the interval of convergence on a geometric series, we just have to take the absolute value of the R value here and set that less than 1. And now we just have to solve for x. So I can do that by multiplying by 4. So I have x minus 1 squared less than 4. And then square rooting both sides, I can write x minus 1 less than 2. Now I just put this in my double inequality notation. So rewriting this without the absolute value, we can write this as negative 2 less than x minus 1 less than 2. Adding 1 everywhere, we have negative 1 less than x less than 3. And because we know that a geometric series has no ambiguity at the endpoints, those are never included, this is going to be our interval of convergence. There's no need to test the endpoints on this. For this one, trying to find the interval of convergence for this series, since this is not quite a geometric series because of the n plus 1 and the 2n plus 1, I'm going to have to use the ratio test for this. So I'm going to have the limit as n approaches infinity of absolute value of n plus 1th term of this, and we're dividing that by just the nth term. So n plus 1th term, I'm going to have n plus 1, so I guess n plus 2. Here this is going to be 2x plus 1 to the n plus 1. And down here, I'm just going to have 2 parentheses, n plus 1, plus another one in there, and 2 to the n plus 1. So all of that. And I have a little bit more simplifying I'm going to do with this term down here. This just kind of looks weird, but we'll get there when we get there. Now, that's just the numerator. In the denominator, I just have the nth term, which is just going to be this original summand. So this whole thing just goes down there. All right, time to simplify this a little bit so we can take the limit. So multiply by the reciprocal. In the numerator, we have n plus 2, 2x plus 1 to the n plus 1 times 2n plus 1 times 2 to the n. And in the denominator, I'm going to rewrite this stuff as, let's see here, 2n plus 2 plus 1, so that's really 2n plus 3, 2 to the n plus 1, and also we have an n plus 1 and 2x plus 1 to the n. I know it kind of all sounds the same when you say it out loud, so just look carefully at what we have upstairs and downstairs. So at this point, we can cancel out a few things. These 2 to the n and 2 to the n plus 1 pieces here, those can reduce to give me just a 2 in the denominator. And same idea with these 2x plus 1s. These reduce to give me just a 2x plus 1 in the numerator. So when the dust settles, I have in the numerator a 2n plus 1, an n plus 2, and a 2x plus 1. Denominator, I have the 2n plus 3. I have a 2 from this reduction, and I still have this n plus 1 as well. The 2x plus 1 we said got reduced with the 2x plus 1 up here, so that's not in the denominator anymore. Okay, well, as n approaches infinity, this plus 1 next to the n in here, this plus 2, this plus 3, and this plus 1, since those are in parentheses with n's and n is getting super big, we can ignore those constants that are being added in there. So I really just have 2n times 2x plus 1 upstairs. So I guess I could call that 2n squared times 2x plus 1. And downstairs I've got, let's see here, this is going to be 4n squared when all is said and done. So 2n squared over 4n squared is just going to reduce to 1/2. And we still have that 2x plus 1 constant sort of along for the ride. So we have absolute value of 2x plus 1 over 2 when all is said and done. Now for the series to converge, this nth ratio has to be less than 1. So we'll set the absolute value of that less than 1 and solve for x to get the interval of convergence, at least the temporary, the first draft of the interval of convergence. So if I multiply both sides by 2, and then really at this point I have to rewrite this without the absolute value. I guess I could divide by 2, but let's just rewrite it without the absolute value. So then I can write negative 2 less than 2x plus 1 less than positive 2. And next I'll subtract 1 everywhere. So this is negative 3 less than 2x less than 1. And if I divide everything by 2 after that, then I've got negative 3 halves and 1 half. At this point, though, I haven't quite got the interval of convergence. We've sort of got it. We've got some endpoints, but we don't know whether this series converges at the endpoints or not because the ratio test is ambiguous with endpoints. We don't really know what happens, what it really means if this whole absolute value were to come out to a value of exactly 1. So we're going to have to test negative 3 halves and 1 half in the original series and verify whether the series converges or diverges with those plugged in. So let's say that x equals negative 3 halves. If I plug negative 3 halves in for x, let's see what happens. So you have 2 times negative 3 over 2. That's going to be negative 3. Negative 3 plus 1 is going to be negative 2. So you can combine negative 2 to the n and 2 to the n together. That gives you basically negative 1 to the n, and you still have the n plus 1 and the 2n plus 1 hanging around. Now, we're going to always try the nth term test whenever we start things. It's always a good idea to see if your nth term is at least approaching 0 or not. So if I take the limit of this whole thing as n approaches infinity, I see here that I've basically got plus or minus n over 2n if we ignore the plus 1 and the plus 1 down here. So that really just reduces to plus or minus 1 half. This is not 0, so this is going to diverge by the nth term test. So what this means then is that this less than symbol with the negative 3 halves is going to remain less than. We're not going to write an equals under there because we diverged at that endpoint. Now let's test out the endpoint x equals 1 half. So if we plug in 1 half to the original series, 2 times a half is just going to be 1. 1 plus 1 is 2. And we have basically 2 to the n over 2 to the n, which just cancels out. So with 1 half for an x value, this series can just be written as n plus 1 over 2n plus 1. If we try the limit of this thing as n approaches infinity, again running our nth term test, we see that this comes out to just 1 half, which again is not 0. So this also diverges by the nth term test. And then our final interval of convergence is going to have just strictly less than symbols. So negative 3 halves less than x less than 1 half. And that's it. For this problem, I'm trying to find the interval of convergence for this series. So because this is not a geometric series, not quite because of this n factorial, I'm going to have to use my ratio test. So finding the nth ratio, let me take the limit as n approaches infinity of the absolute value of n plus 1th term over the nth term. So that's going to be an n plus 1 factorial. We have an x to the 2n plus 2, and we have a 2 to the n plus 1 in the denominator there. And I could write 2n plus 2. I haven't quite done that yet, but it's going to happen. Now downstairs here we just have the nth version of this, which is pretty much what you see in the summand here. Just n factorial, x to the 2n, and 2 to the n. Multiplying by the reciprocal to simplify this, I've got n plus 1 factorial, x to the 2n plus 2, and 2 to the n in the numerator. Downstairs I have 2 to the n plus 1, n factorial, and x to the 2n. Doing a little simplifying, the 2n and 2 to the n and 2 to the n plus 1 can reduce. That leaves us with just 2 to the first power in the denominator. These factorials can reduce, leaving me with just n plus 1 up here. And these x to the powers can also reduce a bit. So if I subtract 2n from 2n plus 2, I end up with just x to the 2, x squared, in the numerator. So putting things together now, we have an n plus 1 and an x squared upstairs. And downstairs we still have a 2, and that's actually it. So as n approaches infinity, this numerator is going to grow without bound, and the denominator is not growing at all. So this whole thing goes to infinity. Now, to converge, the nth ratio of this series needs to be less than 1. Well, it isn't. So there's really going to be no interval of convergence. The only thing we're going to converge at is going to be the center of the series, which you get for free. In this case, since we just have an invisible x minus 0 being raised to this power, your center is just going to be x equals 0. If you plug 0 in for x, that would zero out this whole summand, and you would just be adding 0 over and over again, which would be a form of converging. So we have x equals 0, and that is it, nothing else. For this one, trying to find interval of convergence, I'm going to start, since I noticed that we have a bunch of things being raised to the n, I'm going to start by rewriting this as x plus 3 squared over 16, one big fraction there, all raised to the nth power. And when I do this, I see that I actually have a geometric series, which makes my life a lot easier on this, because I can take the r value, which is x plus 3 squared over 16, the r value of this geometric series, and to find the interval of convergence, I just need the absolute value of this to be less than 1. Okay, so I'm just going to solve for x at this point. Start by multiplying by 16, and then square root both sides to get 4. So we have x plus 3 absolute value is less than 4. Rewriting this without the absolute value, we have negative 4 less than x plus 3 less than 4. And then subtracting 3 everywhere, this will be negative 7 less than x less than 1. Now the nice thing about geometric series is that you never have to include the endpoints with these. So once you get this, we are actually done. We don't need to test out negative 7 and positive 1 for convergence. To find the interval of convergence for this one, we're going to have to use the ratio test, since this is not a geometric series. So I have the limit as n approaches infinity of absolute value of n plus 1th version of this. So that's x to the 2 parentheses n plus 1 over n plus 1 factorial, which we'll clean up a little bit in a minute. So dividing that by the nth term of this, which is essentially just whatever you see in the summand here originally. And now let me do a little same change flip to start simplifying this. So I'm going to rewrite this as x to the 2n plus 3, because we have 2n plus 2 plus another 1. So x to the 2n plus 3 times n factorial. That's going to be my numerator there after I multiply by the reciprocal. And in the denominator, I have this x to the 2n plus 1 and this n plus 1 factorial. So I can reduce these exponential x terms here. This is going to, let's see, if I subtract the exponents, this reduces to just x squared in the numerator. And these factorials also reduce, leaving me with just n plus 1 in the denominator. So to recap, we have x squared upstairs and just n plus 1 downstairs. Now, as n approaches infinity, this is a bottom-heavy term, so this thing just goes to 0. To converge, the absolute value here of this ratio, this nth ratio, has to be less than 1. Well, 0 is always less than 1 for whatever value here you plug in for x. So that means this is going to converge for all real numbers, so we can write the interval of convergence as negative infinity, less than x, less than positive infinity. For this free response problem, we have a Taylor series for f about x equals 1, given by this expression here. And this, we're told, converges to f of x for absolute value x minus 1 less than r, where r is the radius of convergence. Okay, so we want to find the value of r. In order to do this, we're going to have to use the ratio test on this one. It's not a geometric series, so we unfortunately can't just take a common ratio and set it less than 1. We're going to have to use the ratio test and set the results of that less than 1. So let me take the limit as n approaches infinity of absolute value of the n plus 1th term divided by the nth term. So the n plus 1th term, and we can ignore this negative 1 because we're inside an absolute value. So n plus 1th term, we're going to have 2 to the n plus 1. We're going to have an x minus 1 to the n plus 1, all of that in the numerator. And we have an n plus 1 in the denominator. Now, down below here, we just have the nth term, which is just the original version of all of this. Again, excluding this negative 1 because we're inside absolute value, so it wouldn't make a difference anyway. And now I'm going to simplify this by multiplying by the reciprocal. So in the overall numerator now, we have 2 to the n plus 1, x minus 1 to the n plus 1, all that times n. And in the denominator, we have these two exponential terms, 2 to the n, x minus 1 to the n, and then we also have this n plus 1. I can reduce these 2's to give me just a 2 in the numerator. Same thing with these x minus 1's. I'm going to reduce these to have just a single x minus 1 to the first power in the numerator. So upstairs then I've got a 2, I've got an x minus 1, and I've still got this n hanging around. Downstairs, the only thing left over is going to be the n plus 1. As n approaches infinity, I can ignore this plus 1 down here. So I essentially have 2n x 2x minus 1 times n over just n. The n's are going to cancel, leaving me with just 2 parentheses x minus 1 inside my absolute value. So for the series to converge, this nth ratio that we just found here has to be less than 1. So I'll let that be less than 1. And to get the radius of convergence, we just need to have a coefficient of 1 on x, like they have up here. So I'm just going to divide everything here by 2, and that'll give me absolute value x minus 1 less than 1/2. So since that matches the exact pattern they had up here, that means that r, the radius of convergence, is just going to be 1/2. For this problem part, we want the first 3 non-zero terms in general term of the Taylor series for f prime, the derivative of f. All right, so let's start by writing out just the first 3 terms in general term for f itself, and then we'll take the derivative of whatever we get. So let's see here. First term, plugging in 1 for n. That's going to be, let's see, negative 1 to the 1 plus 1, so that's just positive 1, so we can ignore that. So we have a positive first term. That's going to be 2 to the 1 over 1, so that's just 2 out in front. And then we have x minus 1 to the 1, so just x minus 1. So when all is said and done, our first term is just 2 parentheses x minus 1. Okay, not so bad. Let's move on to n equals 2. So that now makes this negative 1 to an odd power, so we have a negative next term. 2 squared over 2 is just 4 over 2, which is just 2. So we have a negative 2 x minus 1 to the second power. And then finally for the third term, plugging in 3 for n, well now we're positive again because we have an even exponent on the negative 1. This is now going to be 2 cubed, which is 8, over 3, so we have 8/3 x minus 1 cubed. Again, that's positive. And now for the general term, well, that's just going to be this summand that they gave us here for the series. So let's just write that again. Now for f prime, I'm essentially just going to take the derivative of each of these terms using the power rule. So for this first one, I guess I could distribute this to have 2x minus 2, but then the derivative of that would just be a 2. That minus 2 would just go away because it's a constant. So we have just 2 for the first term of f prime. For the next term, this is going to be negative 4 x minus 1 to the first, so we don't have to write the first power, but it's there. And then using the chain rule, there's just a tail of 1, so we don't have to write anything else because of the x minus 1. Over here now, using our power rule, 3 times 8/3 is just going to be 8. So we have 8 parentheses x minus 1 to the second power. And now we have to write the general term. So there's a lot of ways to write this. We know that there's going to be a negative 1 to some kind of power because we keep going from negative to positive. We know there's going to be a 2 involved. These are all powers of 2, 2, 4, and 8. And we know there's an x minus 1 involved as well. We just have to figure out what to write for the exponents. So you have to commit to an n value, a starting n value in the beginning here. I'm going to let my starting n value be, let's make it 1. So if I want this thing to come out positive initially, I need to have negative 1 to the n plus 1 then, so that I start with an even power. I can write just 2 to the n, because then we would have 2 to the first, 2 to the second, 2 to the third. And my x minus 1s, I need to make that, well, let's see, how could I do this? If I'm starting with a power of 1, and I don't want to see an x minus 1 here, I need to have an x minus 1 to the n minus 1, so that the very first thing I have is x minus 1 to the 0. So putting all that together, we have negative 1 to the n plus 1, 2 to the n, x minus 1 to the n minus 1. And if you're not sure, it's always good to plug in a few n values and make sure it actually works out. So let's plug in the n value 2. That would give us negative 1 to the third, which comes out negative. We would have 2 squared, which is 4. We'd have x minus 1 to the 1, which is this here. Let's plug in 3 for n. That would give us a positive for this negative 1 term. We'd have 2 to the third, which is 8. And we'd have x minus 1 to the 3 minus 1, so x minus 1 squared, which is this term. So that works out if we write things like this. And since we've written the derivative, that's it for this part. For this last part of the problem, we receive the revelation that the Taylor series for f prime that we found in part B is a geometric series. No way. Based off this, we need to find the function f prime to which the series converges, and then use this to determine f. Okay, so we've basically got a geometric series that we want to put in just normal function form, and we also want to figure out the function form for f. So let me start by rewriting what we've already gotten so far. So here was the original series in function form, and here was the derivative that we found in part B. So now they said that this f prime here is a geometric series. So for the a1, which is important to know for a geometric series, that's going to be just this initial term of 2. And for the r value, what we're multiplying by each time, it looks like we're multiplying by a negative 2x, or 2 parentheses x minus 1, because 2 times this would give us negative 4x minus 1, multiplied by this again. Now we've got positive 8x minus 1 squared, and so on. So to turn this into an actual function versus a series, we're going to use our infinite sum formula, which is going to be, that's a1 over 1 minus r. So that's our general format for what f prime looks like as a function. And now plugging things in, I can write this as 2 over 1 plus 2 parentheses x minus 1. And since I'm eventually going to need to turn this into an f function, I'm going to simplify this. So this would be 2 over, and let's see here, this is really 1 plus 2x minus 2. So this would be 2x plus 1 then. No, minus 1. There we go. We have a plus 1, we have a minus 2, so 2x minus 1 when all is said and done down there. So now we need to figure out the f function based off of this. Well, if you have f prime, you can get f by taking the antiderivative, or at least that's a good start. So let me take the antiderivative of both sides. Antiderivative of f prime is just f of x. And on the right side, we're taking the antiderivative of 2 over 2x minus 1. So that's going to be 2 ln absolute value of 2x minus 1 divided by the derivative of 2x minus 1, so divided by 2. So we already had a 2 out in front of the ln, so those get canceled out, and we just end up with ln of 2x minus 1, and don't forget the plus c. We're going to have to figure out what c is. In order to do that, we need some kind of initial value. So the key on this one, if you look back at the original series, the only initial value you really know is if you plug 1 in for x, well, 1 minus 1 would give you 0 here. That would zero out everything, and the sum of a bunch of zeros added together is just 0. So we know that f of 1 is going to be 0, because 1 is the center. So this is our initial condition that we can use along with this antiderivative to figure out the value of c. So then I can write that 0 equals ln of 2 times 1 minus 1 in absolute value plus c. And let's see here. This is really ln of 1, which is just 0. So we end up with a c value of 0. Okay, so now it's time to plug that back in to write a more specific particular solution for f of x. Now before I do this, I have to resolve this absolute value. We always have to do this when we do the diff-EQ dance. So I notice that for my initial condition, if x is 1, then 2x minus 1, the stuff inside absolute value, is going to have a positive value. So that means that I can replace this absolute value, which is already going to come out positive, with just a regular parentheses. I don't have to negate everything inside. So for my final function then, I can just write f of x equals ln parentheses 2x minus 1 plus 0, but I'm not going to bother writing plus 0, so just ln of 2x minus 1 then.